And the next speaker is Jonas Eschmann, and his talk is about partially unsupervised deep meta-reinforcement learning.
Thank you. I'm happy to present our partially unsupervised deep meta reinforcement learning approach I've been working on with Claudio Zito and the lab of Jan Peters at the University of Darmstadt. So first of all, the motivation is for this approach is to improve the sim-to-real transfer of reinforcement learning-based agents. We want to improve the sim-to-real transfer because usually it's not feasible to directly train on the real system with trial and error learning because of wear and tear and so on. But the challenge with training in simulation is, as has been said earlier, the reality gap, which always exists between the simulator and the real system, which prevents the direct transfer of agents learned in the simulation to a real system. And one common approach to bridge this reality gap is domain randomization, where a single agent is trained over a distribution of environments. And the assumption is then that the real system is just another sample of this distribution over environments. But the problem with this approach is that the performance of the single agent decreases as we increase the variance over the environments. But this is increasing the variance over environments is desirable because by this we also increase the support of the distribution, which makes it more likely that the real system has been sampled from the distribution. To highlight this problem, here's a simple example where we do domain randomization using broad distributions. So we have the Acrobots environment where we do domain randomization over the link masses of the first and second link. And on the left side, we've trained individual agents for all these different environments. And on the right side, we did the domain randomization approach where a single agent is trained across all of them. And let me just activate the video mode. It's already on. Okay, so here you can see that the single agent across the different environments is not able to learn a single policy which is able to act well in all these different environments. But it can be clearly seen that it's dynamically feasible to to expose a good behavior in all these different environments. And this shows the how these broad distributions can be detrimental to the domain randomization performance. We can also see this from the returns that these agents gain. So in blue, we have the single agent across different environments, and there's a big gap to the single agents in the returns that they are able to attain. And with our work, the goal is to move this line up to approach good performance. The main ideas to accomplish this are first to rephrase domain randomization as meta-reinforcement learning, where the agent can be aware of the environment it is acting within. And then also to evaluate a novel training paradigm, which allows to split the training of the inference of the environment from the learning of the behavior using the reinforcement learning training loop. And some related work is first the learning to reinforcement learn paper, where they coined the term deep meta reinforcement learning, but they are not concerned with domain randomization. Then there's efficient of policy meta reinforcement learning via probabilistic context variables, where the authors focus mainly on qualitatively different tasks, and this approach is also not suitable for domain randomization. And then there's the learning dexterous in-hand manipulation, where the authors train the manipulation of a cube with a high degree of freedom robotic hand in simulation, then actually transfer it to the real world. They do this domain randomization, but they don't separate the training of the inference of the environment from the learning of the behavior. So first of all, where does this underperformance of the domain randomization come from? So we have the normal case where we have the conditional independence of the next state of the previous states given the current state in action. But as soon as we introduce the domain parameters xi, which are not observed, we get a dependence on the previous states and actions because there's an active path in the Bayesian network. So even if we know the current state and action, the next state is dependent on the previous states and actions. Now, because these domain parameters xi are not observed, we model them using dynamics embedding Z, which should capture the same information as the domain parameters, but it might have a different structure. So we don't enforce it to have the same units like masses and so on, but this whole thing should model the same distribution. And looking at the equations where we can incorporate the conditional independences, we can, in the case of the domain parameters, we can marginalize out these domain parameters and get the transition probability. For the case of the dynamics embeddings, we can do the same, and we can see that we model the same probability distribution just now with the dynamics parameters, which capture the same information, but they might have a different structure. So now looking closer at this marginalization over the embeddings, usually this marginalization integral is not tractable, and also we don't want to choose a family of distributions for this posterior over the dynamics embeddings. And because of that, we introduce deterministic function f, which is dependent on the previous states and actions the agent has seen, and outputs z prime, which can be thought of as capturing the sufficient statistics for this posterior distribution. And we can refer to this as the dynamics encoder. So now with the dynamics encoder and the sufficient statistics for the posterior, we can write down a new transition probability, which has this marginalization implicitly in it. And now furthermore, to model this transition probability, we can use a Gaussian observer model where the mean is given by another neural network, which predicts the next state given the current state and action, and also the output of the dynamics encoder. And with this, we can just apply maximum likelihood estimation, and this gives rise to a standard mean squared error regression in the case of the Gaussian observer model. So now we can also draw this into a block diagram where the red parts are trainable, and on the right side we have the classic RL loop, where now there are different environments where the agent is interacting with because of the domain randomization, and we generate data for all of them. And then now we can use the data of one particular environment, the experience, feed it into the dynamics encoder, which for example can be a recurrent neural network, and this then outputs dynamics embedding. And if this dynamics embedding compresses the information from the experience into an informative structure which characterizes the dynamics of the system, the agent can then use it to act better across all these different environments. But now the question is, how do we enforce that this latent space has an informative structure? And to accomplish this, we stick a transition model on top of it, which can be another, just a normal feed-forward neural network. And this tries to predict the next state given the current state and action from the same environment. And to be very good at predicting the next state across all the different environments, it also needs the dynamics embedding to differentiate how the different environments work. And with this complete structure, we can just backpropagate through it and train this as one thing. And in the end, we would discard this transition model and just use the dynamics embedding. So now I will show some results for the latent space. So for the training of the dynamics encoder, these are for the case of a modified pendulum environment where the modes of variation for the domain randomization are first an action inversion parameter, which means that in some of the environments, the torques applied by the agent are multiplied by -1, which is a quite drastic change to the dynamics. And then we also randomize over the masses from 0.1 to 1 kilogram. Here you can see the latent space of the dynamics embeddings before the training, and it's not very informative, but you can see that the different environments are characterized by these points where the shape tells if the actions are inverted or not, and the color, the redness shows the mass. So if it's very red, it's very heavy. Then after training, we get this very informative and very orderly latent space structure where we have a clear separation between the different environments and even a gradual change in the mass in the continuous parameter. So now to the learning of the behavior. We first, our first approach was to use PPO, but then we ran into the issue that it fails in a multitask setup. And we looked it up in the literature, and there were also other authors reporting this. So we switched to the soft actor critic algorithm, and we applied it to the pendulum and acrobot. And first of all, it works well in the multitask setup in comparison to the PPO algorithm. And then it also works well in the partially unsupervised deep meta reinforcement learning setup, as I will show now. So here we have the results for the modified pendulum again, where there are different approaches. The returns of different approaches over the training are shown. So first of all, the blue one is the plain domain randomization, where the agent doesn't have any information about the environment, and the green one is our approach, where we use the dynamics embeddings shown earlier as an input for the agent. And this is almost as good as the multitask learning setup, where the agent receives the ground truth information about the domain parameters. And here we have the resulting behavior, where a single agent is acting across all these different environments for the pendulum. And it uses the dynamics encoder, the information from the dynamics encoder, which at the beginning of an episode starts with zero information, and then quickly builds up the information in the latent space, which is then used by the agent to act well. And we also applied this to the acrobot and even increased the difficulty by also adding the action inversion domain randomization parameter. And you can see that also here, even with the action inversion, which is shown by the white and black dots in the actuated joint, it is able to learn policies, like a single policy, which can swing up and stabilize all of them. So then we also looked at the generalization and extrapolation capabilities, where we are looking at the modified pendulum environment again. And here our main focus is on the generalization, because as told before, we want to have the distribution over environments as broad as possible to capture the real environment, and we don't try to extrapolate from to environments which have not been captured by our distribution. So for us, it's most important that the test samples with environments which have masses that have not been seen during training, there the agent performs very well. But when we go out of distribution, for small masses, it's still acceptable, but for higher masses, up to twice the biggest mass, it's the performance goes down by a lot. So for future work, we are looking at additional evaluations on the acrobot for more domain parameters like friction coefficients and the length of the links. And then also to go for the drone stabilization, where we first implement the drone stabilization using SAC, and then I apply our approach. And then we can try a sim-to-sim transfer using training in a very crude simulator and then transferring to the high fidelity GIM FC simulator, which has been highly tuned by one researcher to fit one particular drone. And if this works well, we can actually try to do the true sim-to-real transfer. Okay, so with that, I conclude, and I'm happy to take questions.
Thank you, Jonas. Excellent presentation. As usual, I would wait for a few seconds to see if any question appears in the Q&A. Otherwise, I start asking, given that we are, as you know, a bit late. So I'm wondering, so you have, I mean, I do see the applications of this approach in robotic settings to problems such as, I don't know, stabilization and so on. But I'm thinking, if in robotics you would have a totally different problem that cannot be modeled like an inverted pendulum. So you have something, I don't know, name it, navigation, something. How do you go back to your meta-reinforcement learning modeling, and what do you change to model a totally different problem, so different dynamics? What components do you need to change for this?
Yeah, I would say so. If the state is observed in a similar way to these robotic arms or to these environments, then I would say it's more or less a straightforward transfer. Where it gets a bit more challenging, or where there would be maybe a completely different approach would be needed, is when the observations are, for example, images, where I think it would not make sense to have this transition model as a target function to train the dynamics encoder, because you would need to train a completely generative model for images. So there you probably would need another approach. But I think for all the approaches where the actual state can be observed very well, I think it is more or less directly applicable.
So if there is no more question, I would like to thank Jonas and again make a round of applause virtually.